Wind over the sea surface makes waves like these, wind waves. In the open sea, the waves have a confused appearance. The waves run with the wind, but in a disorderly way, with ridges and valleys growing and declining and sliding in many directions. At sea, waves of all lengths are formed up to the maximum for any given wind speed. These waves are all mixed together. The constant slight changes always found in wind direction add to the confusion. As they run towards the shore, the disorder of the waves is reduced by the shallowing water, and the waves become simple rows. Such waves of simple outline can be defined first by their length and height. Each passage of a wave is called a period, written T. That is, the time it takes to travel past a fixed point. The celerity, or speed of a wave, can be expressed as the length L over the period T. If celerity, wavelength, and period are all related, then these waves, with a 7-second period, must be 250 feet long and traveling at 25 miles an hour. The celerity is also related to the length alone, and is in fact proportional to the square root of the length. So the longer the wave is, the faster it travels. We can generate waves like wind waves in an experimental tank. These are simple waves of fixed wavelength, shown here in slow motion. We start to get shapes resembling sea waves if we make the waves in the tank of different lengths. These complex waveforms can in turn be resolved back into a spectrum of simple waves. Waves do not flow like currents. Although the waves move forward with a certain celerity, the water they contain does not move forward with them. Instead, it moves round vertically in a nearly circular orbit, so that when the wave has passed, the water is almost back where it started. At the surface, the diameter of the orbit is the same as the wave height. Below the surface, the orbit gets smaller and smaller. At a depth of 1 wavelength, it's about 1/500th of the surface orbit. Below this, the water is practically still. If we increase the wave height, the speed of the orbiting water increases. It increases too as the period becomes shorter. The fastest orbiting speed is produced by short, high waves. Celerity too depends on wavelength, but in the opposite sense, for shorter waves mean lower celerity. There may come a point when orbital speed exceeds celerity. Then the water at the top of the wave is moving faster than the wave profile, so it leaves the profile and shoots forward, sliding down the front of the wave. That is, the wave breaks. When this happens, the ratio of height to length is about 1:7. Half a wave's energy is potential. This is the potential energy, its divergence from the horizontal. It lies in the wave's form and moves forward at the wave's celerity. Half a wave's energy is kinetic. It moves only in circles and stays behind when the waveform has passed. Here we've drawn a train of waves. For simplicity, they are all of the same length and height. As the first wave moves into still water, it molds this water into a wave shape. This wave shape has become smaller because it's left its kinetic energy behind, and so only half the energy goes to make the new wave. Each wave picks up the kinetic energy of the one in front and leaves its own behind. The kinetic energy of the last wave goes to make another wave, smaller, because it needs both kinetic and potential energy. The wave train first formed had its middle wave here. The waves have moved one wavelength to the right, but because an extra wave has been added at the back, the middle of the wave train is not one wavelength further on, but only half a wavelength. That is, the group of waves, taken together, is travelling only half as fast as the individual waves. What happens at sea is that the leading waves keep getting smaller and dying out, and waves from the back appear to run through the group at twice the group velocity until these in turn reach the front and fade out. The coastline has a special effect on waves. On this shore, a strong wind is blowing, but the waves are small. Further out to sea, the waves are bigger because the wind has longer to act on them in its passage over the water, until a point is reached where the waves attain a maximum height possible for this wind speed. Such a distance may be a few yards or many miles, depending on how strong the wind is. The distance of any wave from the windward shore is called its fetch. Here, the fetch is many miles. So wave heights depend not just on wind speed, but also on sufficient generating distance, on fetch. The largest waves are found far from the wind's origin, where the fetch is large. Empirically, height is proportional to the square root of the fetch. Sometimes the fetch is not enough for the maximum waves to be generated, because the body of water is small. So we don't find very big waves in the boating lake, even in a gale. Here are our main points again. The confused outline of the sea surface can be resolved into many ideal waves of different heights, lengths, and directions. In an ideal wave, celerity is equal to the length over the period. Also, celerity is proportional to the square root of the length. As the height increases, particle speed surpasses celerity. Then the crest shoots forward and the wave breaks. In deep water, the diameter of the surface orbit is equal to the wave height, but orbit size decreases until below a depth of one wavelength, the water is still. Half a wave's energy is potential in the waveform. The other half is kinetic in the orbiting particles. Energy is lost from the front of the wave train and left behind at the back. Group velocity is thus only half the celerity of individual waves. In shallow water, waves are slowed down until at last the celerity becomes independent of wavelength and depends only on depth. As the bottom shelves, celerity decreases more and more. Finally, the wave breaks. This seems to happen when the water depth is about 4/3 of the wave height. The breaking point for the largest waves in the spectrum is called the plunge line. Waves in shallow water do not have spilling crests like deep water waves, but curl right over and drop. From here, the orbit motion ceases, and the surface water moves bodily forward. In compensation, bottom water gravitates seaward. If the waves have been big enough, the bottom water can drag part of the beach with it, eroding it away. Conversely, small, gentle waves will build the beach up again. Winter gales are destructive, summer breezes constructive. Wave action molds much of our coast. Waves can build up the shore by gentle flow, or hammer it back by attacking it strongly. A coast that is being eroded by the sea has a steep profile. High waves can beat on it and eat it away, especially at the base. Then the cliff falls into the sea. If the attack is uneven because of the shape of the shore, or if parts of the cliff are harder than the rest, they will not fall back so quickly, but remain behind to form headlands, or they may even form isolated stacks. The headlands form anchors for the sandy bays between. As long as the headlands stand firm, the beach between is much more stable than it looks. But if the headlands are cut back, the beach sinks back with them. Here's how this attack on the anchors is mounted. Waves running inshore may often be oblique to the coast. As they enter shallow water, the inside edge of the wave is slowed down. This twists or refracts the wave towards the shore. A headland jutting out into the sea has waves turning inwards onto it from both sides. In the bays, the waves are fanned outwards, and so their force is spread more widely and the pounding is reduced. Another look at the headland shows more clearly what happens to the wave patterns on this kind of coastline. All the waves from this part will concentrate on the headland, while waves from this part spread out into the bay. Moreover, the seabed around the headland usually shoals more steeply than in the bay, so the waves there lose their energy more abruptly and with greater damage. So the headland is under severer attack than the bay. Waves have a profound effect on the life of the seashore. In quiet, sheltered water, the height of the shore is small, not much more than the tidal range. Attached seaweeds grow luxuriantly, and there is a great variety of animal life. On soft shores, wave action can sort the grains of sand and mud. In sheltered bays, many of the small mud grains remain. In these conditions, we get animals like this typical mud-dwelling bivalve mollusk. If the waves are vigorous, the small mud grains are washed away in suspension, and a clean, sandy beach is left. It has its own characteristic fauna, mostly of small worms. On some shores, waves can kill all life. The pebbles are ground about by the sea, and nothing survives. A pebble beach is a dead beach. An exposed shore is extended by waves to well above the high water mark. It has no large weeds, for they would be torn away. Instead, the rocks are covered by tough barnacles and limpets. Waves help to shape the shore and to decide its extent, and they control the kind of life found on it. Waves driven by wind, whether fair wind or gale, this is the sea's motion throughout all the oceans of the world.